Right now, in a spectrum of light reflected off the frozen surface of Pluto, there is a line that should not be there. No known molecule in any solar system body, any exoplanet atmosphere, any laboratory reference catalog on Earth produces this exact signature. No astronomer who has examined it can currently name what is making it. It is not a glitch, it is not noise. It is a real, repeatable physical signal. And it is not one thing happening on one distant world. It is happening on two. Stay with me, because by the end of this, the honest answer is still, we don't know. If you're new here, this channel breaks down real space missions using only verified, peer-reviewed science. So, if that sounds like your thing, subscribe. It's free. Let us go back to the beginning. To understand why an unidentified absorption line on Pluto is such a big deal, you have to understand how little direct light we've ever collected from that world. For most of the 20th century, Pluto was a smudge, a single pixel of light, discovered in 1930 by Clyde Tombaugh, too small and too far to reveal any surface detail at all. That changed only once, dramatically, in July 2015, when NASA's New Horizons spacecraft became the first and only mission ever to fly directly past Pluto, sweeping within about 7,800 miles of its surface and beaming back images that revealed mountains of water ice, a heart-shaped nitrogen glacier called Tombaugh Regio, and a thin, hazy blue atmosphere nobody had properly modeled before. But New Horizons was a flyby, not an observatory. It had one shot, moving at roughly 31,000 miles per hour, and then it was gone, hurtling onward into the Kuiper Belt. Everything learned since 2015 has had to come from somewhere else. And for the fine-grained chemistry of Pluto's atmosphere and surface, that somewhere else is the James Webb Space Telescope. Webb, which launched on December 25th, 2021, and reached its observing post nearly 1 million miles from Earth the following month, was never designed as a Pluto telescope. Its primary mission is aimed at the deepest, oldest galaxies in the universe and the atmospheres of planets around other stars. But one of its 4 instruments, the mid-infrared instrument known as MIRI, happens to be extraordinarily good at something else entirely, splitting the faint light bouncing off cold, distant worlds into a detailed spectrum and reading, wavelength by wavelength, exactly which molecules are present. Here's the basic physics, stated plainly, because it matters for everything that follows. Every molecule absorbs light at very specific wavelengths, like a fingerprint. Methane has its signature, nitrogen ice has its signature, carbon dioxide has its signature, and scientists have spent decades building reference libraries of exactly where those fingerprints sit. When astronomers examine the reflected light of a distant world and see a dip, a specific wavelength, where less light comes back than expected, they can usually match that dip to a known molecule and say, with real confidence, that's there. Oh, yes. That is how Webb has already confirmed water vapor and carbon dioxide in the atmospheres of exoplanets trillions of miles away. The method works. It is trusted. It is not speculative. It's worth being fair to why the old picture of Pluto held up as long as it did. For most of the space age, Pluto simply wasn't a priority. It's small, smaller than Earth's own moon, and so distant that even Hubble, launched in 1990, could only resolve it as a handful of blurry pixels. Sending a dedicated mission made sense only once, and NASA committed to exactly that with New Horizons. It launched in January 2006 specifically to reach Pluto before its thin atmosphere, tied to its slow orbit around the Sun, potentially froze onto the surface entirely as Pluto moved farther from sunlight. That single flyby in July 2015 rewrote the textbook overnight, but a flyby by definition captures one narrow slice of time and one narrow set of instruments. It could photograph the haze. It could not sit and watch it change, season by season, the way an orbiting or Earth-based observatory eventually could. That's the gap Webb was built to fill for worlds across the solar system generally, and it happens to be extraordinarily well suited to fill it for Pluto specifically, which is exactly why what happened next is worth taking seriously rather than dismissing as hype. This was never going to be a case of Webb seeing something weird in a blurry image. It was a case of Webb collecting a precise measurement in a wavelength range barely explored before now, and that measurement simply not matching anything in the reference books. Read that again, because the distinction matters. This isn't an unexplained shape. It's an unexplained absence of light, at one exact wavelength with no known cause. Before we get to that unexplained line, though, there's a discovery from the same instrument, the same mission, examining the same tiny world that scientists actually did predict correctly, and the story behind it is almost as strange as the mystery that followed it. Back in 2017, 2 years after the New Horizons flyby, a planetary scientist named Shi Zhang at the University of California, Santa Cruz, looked at the flyby data and proposed something that sounded, by his own later admission, close to absurd. Pluto's atmosphere is a thin mixture of nitrogen and methane, sitting at a surface pressure roughly 100,000 times weaker than Earth's. thin enough that if you stood on Pluto's surface unprotected, the air around you would barely register as air at all. Photochemical reactions in that thin gas produce a haze, fine particles drifting through the upper atmosphere. Conventional planetary science says haze warms a world, the way smog traps heat over a city. Zhang argued the opposite, that on Pluto, this haze was doing something almost nobody else's model accounted for, actively cooling the atmosphere, radiating heat away into space through the exact particles everyone assumed would trap it in. His peers, by his own account, were skeptical. It was, in his words, a crazy idea. But Zhang did something every good scientist should do with a controversial claim. He made it falsifiable. If the haze really was cooling Pluto's atmosphere the way he described, he said, it should be emitting a specific strong signal in mid-infrared light, a signal no instrument built before Webb had the sensitivity to detect. Think about what that actually requires as a scientific bet. Zhang wasn't just guessing that haze mattered. Plenty of scientists already suspected that. He was making a specific, falsifiable claim about the direction of an effect that ran opposite to intuition, staking his credibility on a signal that literally could not be checked with any instrument that existed at the time he proposed it. That's a very different kind of claim than most predictions that get discussed after the fact, dressed up in hindsight to look more confident than they were. This one had a number attached, a wavelength range attached, and a built-in admission that it would sit untested for years. Sit with that for a second, because it means Zhang effectively wrote a prediction in 2017 for a telescope that would not even launch for another 4 years. Webb reached orbit in 2021. It took until spring of 2025 for a team led by Tanguy Bertrand at the Observatoire de Paris to finally point MIRI at Pluto and Charon long enough and precisely enough to test it. On June 2, 2025, their results were published in Nature Astronomy. The mid-infrared thermal signal was there, exactly where Zhang said it would be. Here's where it gets genuinely strange. Haze particles that both absorb sunlight, heating up, and then re-radiate that heat away in the infrared, cooling the surrounding gas. A self-regulating atmospheric thermostat, unlike anything confirmed anywhere else in the solar system. Zhang, reflecting on the confirmation, said something worth remembering for how rare this kind of moment actually is in planetary science. It is not common, he noted, to see a hypothesis confirmed within just a few years of proposing it. Most predictions in this field wait decades for the right instrument to come along, if they're ever tested at all. This one waited 8. Here is where this stops being an abstract curiosity about a dwarf planet 3 billion miles away. The same haze chemistry driving Pluto's thermostat, nitrogen, methane, and hydrocarbons interacting under sunlight to form organic particles, is, according to the researchers on this project, structurally similar to what scientists believe surrounded early Earth, long before oxygen filled our atmosphere and before life as we understand it existed. Pluto's atmosphere is, in effect, a working laboratory for the kind of chemistry that may have set the stage for the origin of life on our own planet, running in real time, 10 billion kilometers away, cold enough that nothing about it changes quickly. Understanding how haze particles there heat, cool, and cycle molecules between atmosphere and surface gives scientists a live analog for questions about Earth's own nuclear-powered rotorcraft lander roughly the size of a small car, designed to fly from site to site across Titan's surface, rather than sit fixed in one place, is scheduled to launch no earlier than 2028, and, if its trajectory holds, is projected to arrive and begin flying through Titan's atmosphere in 2034. Dragonfly will carry its own onboard mass spectrometer, an instrument built to directly sample and identify surface material rather than infer its composition from reflected light nearly 1 billion miles away. If the mystery compound sitting on Titan's trailing hemisphere is real and abundant enough to detect up close, Dragonfly could, in principle, name it directly. And because researchers already suspect the same substance exists on Pluto in even greater concentration, confirming it on one world could effectively confirm it on both, resolving from the ground what Webb could only flag from deep space. That's the honest state of the science, and it deserves to be said plainly rather than smoothed over for the sake of a tidier ending. The 5. 11 micrometer signal has not been published in a peer-reviewed journal. The leading candidate explanations, a modified benzene mixture, acetylene ice, ketene ice, are each physically plausible and none is confirmed. It's entirely possible the follow-up analysis identifies the compound within the next year using existing archival data nobody has fully mined yet. It's equally possible the answer doesn't arrive until Dragonfly's spectrometer gets close enough to Titan's surface to measure it directly in 2034, nearly a decade from now. Real, competing explanations. A genuinely open question. No confirmed resolution yet, on either world, and no way to responsibly claim otherwise. Zoom out from the specific chemistry for a second, because there's a pattern here that shows up again and again across the history of planetary science, and it's bigger than one dwarf planet or one unidentified molecule. Every major leap in understanding the solar system has come not from a single instrument built to answer a single known question, but from an existing tool, pointed somewhere unplanned, catching a signal nobody wrote into the mission proposal. Webb was built to study the deepest galaxies in the universe and the atmospheres of planets orbiting other stars. Nobody designed it around Pluto's haze thermostat, and nobody designed it to find an unidentified molecule shared between a moon of Saturn and a dwarf planet on the edge of the Kuiper Belt. Those discoveries happened because the instrument was good enough, patient enough, and precise enough to notice something small and strange, sitting quietly in data collected for other reasons entirely. That is what real scientific progress usually looks like up close. Not a triumphant announcement engineered on schedule, but a careful reading of light that refuses to match the textbook, followed by scientists honest enough to say so instead of forcing an answer that fits. There's a second, quieter lesson buried in this same story, and it's about how fragile that entire process actually is. One misdiagnosed mechanical fault, one wrong command sent to a grading wheel a million miles from the nearest repair technician, and neither the haze confirmation nor the mystery molecule ever gets found. Not delayed, gone, permanently, for the entire operational life of a telescope that took decades and billions of dollars to build. The line between humanity confirms a controversial hypothesis about a dwarf planet's atmosphere, and humanity quietly loses an entire category of its best infrared science was, for about 10 weeks in 2022, thinner than most people watching Webb's headline images ever realized. Here's an image worth sitting with as this story closes, because it hasn't closed at all. In July 2015, as New Horizons swept past Pluto for the only time humanity will likely manage in most of our lifetimes, one of the last things its cameras captured was Pluto shrinking behind it. A thin, hazy blue ring of atmosphere backlit by the sun, wrapped delicately around a world that took 85 years just to be seen clearly for the first time. That haze is the same haze Xizhong modeled in 2017, the same haze Webb's MIRI confirmed was cooling Pluto's atmosphere in 2025, and it now shares its surface in some small, unidentified way with a wavelength of missing light that no laboratory on Earth has ever cataloged. Somewhere in that thin blue ring, in the frozen ground beneath it, sits a molecule with no name, waiting roughly 1 billion miles from anyone who could tell you what it is. It has been there, unbothered, for longer than human beings have existed to wonder about it, and it will keep waiting patiently, whether the answer comes from a fresh look at archived data next year or from a spacecraft's spectrometer, skimming Titan's dunes in 2034. So here's everything in order. Pluto was barely a smudge in a telescope for 85 years until New Horizons flew past it once in 2015, and Webb's MIRI instrument has been doing the fine chemical work ever since. In 2017, Xizhong made a crazy prediction about Pluto's haze acting as an atmospheric thermostat, and in June 2025, Webb confirmed it exactly as described. That confirmation only happened because engineers managed to save MIRI's most precise spectroscopy mode from a mechanical failure in 2022 that could have ended it permanently. And in June 2026, using that same saved capability, researchers found an absorption line at 11 micrometers on both Pluto and Titan that matches no known molecule in any reference catalog on Earth. A real unresolved mystery, still awaiting either new analysis or NASA's Dragonfly mission, which won't reach Titan's surface until 2034. If you want to know the moment this actually gets identified, subscribe and turn notifications on, because I'll be covering it the second a real answer surfaces, whether that's next year or the year Dragonfly lands. One question before you go. Do you think this mystery molecule turns out to be something mundane we simply haven't cataloged yet? Or something genuinely new to solar system chemistry? Let me know in the comments. I read every single one. Deep past that no experiment on this planet can fully replicate, because Earth's early atmosphere is long gone, replaced generations over by the air we breathe now. Pluto's hasn't gone anywhere in over 4.5 billion years. Every terrestrial rock record of that period on our own planet has been melted, subducted, weathered, or buried by 4.5 billion years of geology and eventually biology. Pluto offers something Earth cannot, a version of that early chemistry left running, largely undisturbed, in cold storage at the edge of the solar system. None of that confirmation, the haze, the thermostat, the 2025 paper, would exist at all if a single mechanical part inside MIRI hadn't been fixed 3 years earlier, and the story of how close that instrument came to losing its most important capability is one most casual coverage of Webb skips entirely. On August 24th, 2022, less than 2 months after Webb's first science images were released to the public, engineers preparing MIRI for a routine observation noticed something wrong. One of the instrument's grading wheels, a mechanical component that rotates to select which wavelength range the spectrometer examines, essential to the exact medium-resolution spectroscopy mode that would later be used on both Pluto and the mystery molecule, was exhibiting increased friction. Engineers at the time described it plainly as sticky. This was not a minor inconvenience. Webb sits nearly 1 million miles from Earth, orbiting a gravitational balance point called the second Lagrange point, permanently beyond the reach of any repair mission. There is no astronaut who can fly out with a wrench. There is no shuttle mission, no spacewalk, no physical intervention of any kind available. Whatever went wrong with that wheel would have to be understood, and if possible fixed, entirely through commands sent across nearly 1 million miles of empty space, with engineers reasoning blind about a mechanical part they could never touch again. Every command sent to Webb takes roughly 3 seconds to arrive one way, not the days-long delays of a deep space probe, but still enough that engineers can't watch a mechanism move in real time and react instantly if something goes wrong. Diagnosing a sticky wheel 1 million miles away means reconstructing its behavior entirely from telemetry, rotation speed, torque readings, tiny deviations from expected performance, all translated back into a physical story about metal parts nobody on the team would ever see or touch again. Get the diagnosis wrong, push the wheel too hard trying to test it, and there was a real risk of turning a manageable friction issue into a permanent jam, an entire observing mode lost for the rest of the telescope's operational life, whether that ended up being 5 more years or 20. The team paused all science observations using that specific mode immediately. An anomaly review board convened on September 6, 2022 to determine what was actually happening inside the mechanism, and whether it could be trusted to operate again at all. For weeks, specialists dug through the wheel's design history, comparing pre-launch testing data against what the instrument was now reporting from deep space, hunting for a root cause without ever being able to physically inspect the hardware. Here's where it gets worse before it gets better. Medium-resolution spectroscopy wasn't a minor feature of MIRI. It was, and still is, the only configuration on the entire observatory capable of the kind of fine spectral detail needed to separate a real molecular fingerprint from background noise in the mid-infrared. Precisely the capability that would, 3 years later, catch Pluto's haze thermostat, and 4 years later catch an absorption line nobody could identify. If that wheel had failed permanently, an entire category of Webb's most valuable science closed off indefinitely on a telescope with a design life measured in years, not centuries. The investigation eventually converged on a specific physical explanation. Increased contact forces between subcomponents inside the wheel's central bearing assembly under certain operating conditions. Not a catastrophic failure, but a mechanical quirk that could be managed if the team changed exactly how and when the wheel was commanded to move. Engineers developed a new set of operational parameters, essentially a gentler, more deliberate way of asking a 50-year design philosophy machine to do something it hadn't quite been built to do this precisely. On November 2nd, 2022, they ran an engineering test built specifically to demonstrate that the new approach worked. It did. Within days, NASA announced that medium-resolution spectroscopy was returning to full science operations, timed, almost poetically, to also catch a rare, real-time opportunity to observe Saturn's polar regions. The mode that would later confirm a scientist's 8-year-old crazy idea, and later still detect a molecule nobody could name, had come within one stubborn mechanical bearing of never operating reliably again. Here is what is happening right now in 2026. On June 11th, a team of researchers uploaded a new paper to the preprint server ARSchiff, meaning it has not yet completed formal peer review, a distinction worth holding on to as this story develops. Digging into a range of very short mid-infrared wavelengths that had been largely unexplored in previous Webb observations, the team found something odd sitting in the spectra of 2 completely different worlds, a distinct absorption line at approximately 5. 11 micrometers, present in the light reflected off both Pluto and Saturn's giant moon Titan. That in itself would be unremarkable if the line matched a known compound. It doesn't. The researchers combed through existing published catalogs of molecular absorption features and reported in their own words that they could not find any referenced band corresponding to the location of this particular signal in either world spectrum. What most people are not seeing when this story gets simplified into a headline is how carefully constrained that statement actually is. Not, we don't know what this is, full stop, but we checked every documented candidate we have access to, and none of them fit. Oh, to be precise about what matched nothing actually means here, astronomers didn't just glance at one chart and shrug. They cross-referenced the observed absorption feature against the published molecular band catalogs used across the entire field of infrared planetary spectroscopy. The same reference libraries that let researchers confidently identify water, methane, and carbon dioxide on worlds trillions of miles away. Coming up empty against that library isn't a minor gap. It's a strong signal that whatever is sitting on Pluto and Titan's surfaces either hasn't been measured precisely enough in a laboratory here on Earth to make it into those catalogs, or is some combination of known ices and hydrocarbons mixed in a way nobody has replicated and recorded yet. The strangeness compounds when you look at where specifically the signal is showing up. Titan and Pluto are, on paper, deeply different places. Titan is Saturn's largest moon, bigger than the planet Mercury, and the only body in the solar system besides Earth known to have liquid rivers, lakes, and even rain on its surface, although its liquid is methane and ethane, not water. Pluto is roughly half Titan's size, permanently frozen, orbiting nearly 4 times farther from the Sun than Saturn itself. The researchers determined the molecule responsible sits on the solid surfaces of both worlds, not in their atmospheres, and even there the behavior diverges. On Pluto, the absorption line is roughly 3 times thicker than on Titan, suggesting whatever this substance is, it's far more abundant on the dwarf planet's surface. On Titan, it isn't evenly spread at all. The signal is noticeably stronger on the moon's trailing hemisphere, the side facing away from its direction of travel around Saturn, then on the leading side facing forward into its orbit. Here's where it gets worse before it gets better. 2 worlds, radically different sizes, temperatures, and locations, somehow sharing a chemical signature that matches nothing in the known reference library, distributed unevenly across their surfaces for reasons nobody has explained yet either. The team has proposed a handful of candidates worth naming carefully as hypotheses rather than answers. One possibility is benzene, a simple ring-shaped hydrocarbon already known to exist in small amounts on icy outer solar system bodies, potentially mixed with some additional, still unidentified compound that shifts its signature just enough to explain the mismatch. Another is some form of acetylene or keton ice, both plausible photochemical byproducts of the kind of nitrogen and methane atmospheric chemistry both worlds share. None of these has been confirmed. All of them remain candidates precisely because none of them cleanly explains everything the data shows. There is, at least, a real dated opportunity on the horizon to settle this from the ground up rather than from 100 million miles away. NASA's Dragonfly mission.